is so now let's say about the next concept is we have defined an open set. Now with the help of this open set, I've started this, how I have defined this open set, what is the idea is come, is we are saying that if we are sitting on, when I can say I'm sitting on a open room, okay. The same concept will also gives me idea that how we can define a, a point if I pick, which is, it is an interior point of that set. Interior means the point is lies inside. The word inside I have used there. So can somebody suggest me when I can say, if I pick up a point, that point I can say that it is an interior point of that room. So the question is how we can define interior point. That is the next concept. Yes, anyone have any idea to define an interior point?
Sir, if you can find an open sphere around that point,
Yeah,
which is entirely in the set, then
definitely. Yes. So if I want to say that a point X is an interior point of the set A, if this point is a center of some open sphere which is entirely in that set. So ultimately you will have the same as open set, but so if another consequence of the interior point, or if I want to say that about the open set, then if every point is an interior point, then that set is the open set. So another way is to looking at the situation. So let us define first what is the interior. Let us write down the definition. So first you require let x comma d be a metric space. A is a subset of X. A point A it's called interior point of A if it is center of some open sphere contained in A. So it is a center of some open sphere which contained entirely in A. The next definition I can define as an interior of the set. Why this definition is needed? Because we know that every set is not an open set. But can we say that, or can we have some set which is part of the original set, and I can say that that is an interior of the set? For example, right now I am sitting on a closed room. So what will be the interior of this room? In our usual manner, we are saying that I want to decorate my home, or in the same way I can say I want an interior, I want to change my interior of a room. So in the same way, the concept is interior of a set. So what is the interior of a set? Is nothing but the set of all interior point of that set. So what is the interior of a set? Is the interior set of all interior points of A. It's called interior of a set. It is denoted by interior of A. It is denoted by interior of A, or in some of the book they are defining like this, or they are denoting by A with circle. So ultimately, what is this interior of a set A? Is the set of all points in A such that there exists r greater than 0, such that SR of X is a subset of A. Okay, that means for every point of A, there exists some neighborhood which is entirely inside this set. This is known as interior of the set. So set is there and it having the interior inside. We have certain results on this interior. Can somebody tell me what should be the property of this interior? First property, by looking at the definition. Yes, can somebody think of that definition?
Sir, ये always open है sir.
Yeah, the first thing you can just observe that this interior of a set is always an open set. That is the first. Interior of A is open. In fact, it is the largest open set contained in A. What does it mean? એના સિવાય બીજો કોઈ ઓપન સેટ હશે તો એ સેટ આ સેટની અંદર આવતો હશે. So this interior of a set A is the largest open set contained by A. So that is the second statement I can say. The interior of A is an open subset of A which contain every open subset of A. It is the same. Are we same kind of definition have you seen somewhere else in linear algebra? Have you seen some same situation in linear algebra? Some kind of?
Yes sir.
When you defining a span. Yeah, when you are defining the span, a span is also a largest set which contains all its linear combination. બરાબર એના બધા જ means whatever the linear combinations are there, it's all contained by that. So in the same manner, this is the set interior of A is the largest open set which contained by the original set A. The third property is says that A is open if your set A, original set A is open if and only if interior of A is A itself. And the fourth property is say that interior of A is a union of all open subsets of A. So it is union of all open subsets of A, and which also include this statement. One statement, if I prove this one, then it will also include this also. So union, it will be union of all open subsets of A. So let us try to prove this interior of A is always an open set, which is very easy to prove. So the first statement, we are going to prove this to show that interior of A is an open set. So if you want to prove that any set is an open, then you have to start with point in that set. So I will take any x in interior of A. If it is a point in this, then there exists an open sphere SR of X such that SR of X is a subset of A as per the definition of interior of A. For every point, there exists, for every point in this, there exists some neighborhood which is inside that. But this X is an arbitrary point. This X is any point in this interior. So for every point, there will be one neighborhood which is inside A. So I can say since this X is any arbitrary point in interior of A. So can I say that this interior of A is made up of union of all these open spheres? So I can say it is union of SR of X, where your X is an interior of A. So what I can say is this interior is actually union of open spheres. But open spheres are always open. And in the previously we have proved that union of open set is open. So that's why this is an open set. So I can say that therefore the interior of A is an union of open spheres. And therefore the interior of A is an open set. Because the previous results which we have discussed, that in fact I can say that if B is an open, if and only if B is a union of open spheres, that also I can use here, which we have proved in the previous thing. That is, any open set is there which is a union of open spheres. So interior of A is always an open set. Is it true? Also prove the fourth statement. This previous discussion which we have here, which we have discussed here, that is interior of A is a union of this, which also prove the last statement. The last statement says that it is union of open subsets of A. So it proves also that statement, because this each SR of X is a subset of A. So hence the fourth statement is also covered here. Fourth statement is also covered in this statement. So fourth statement is proved. What about the second one? That means it is the largest open set. એના માટે શું કરવું પડે? What you have to do? If I take G is any open subset of A, that is the second statement is you need to prove that interior of A is open subset of A which contains an every open subset of A. That means the first statement is already proved with the this first statement, which contains every open subset of A. That means I am taking now one open subset of A, which is G, and now I want to prove that this G is lies inside the interior of A. So what is my objective? It is we need to prove that, or we want to prove that this G is a subset of interior of A. This is my objective. I've taken any open set, and if I prove that this G is a subset of A, which proves that the every open subset of A, which is entirely in A, in interior of A. That means this interior of A is the largest open set. Suppose that because I want to prove that one side is subset of other, I need to pick one point in G. I have to prove that that point is in this set. So let's say X belongs to G. If it is X belongs to G and G is an open set, therefore there exists some R greater than 0 such that SR of X is a subset of G, and G is always a subset of A. So I can say that X is an interior point of A. That means this X belongs to interior of A, which completes the proof of that G is a subset of interior of A. So if I pick any open set, then that set is entirely inside interior of A. So interior of A is the largest open set contained in A. Okay, and that proves also the second statement. Not second, but second statement, that is each which contains every open subset of A. Now the third statement, we will prove the third one, which says that, so what is the objective to prove the third statement? It says that A is open if and only if interior of A is same as A. One side is obvious. Which side is obvious? Which side is easy to prove or trivial from the previous discussion?
Interior of A is A, then A is open.
Yeah. Suppose that interior of A is equal to A. We have to prove that A is open, but interior of A, we have already discussed that it is open, as interior of A is always open. Therefore, A is open. So one side is trivial. Now conversely, that is, suppose that A is open. So what we need to prove? We need to prove that A is equal to interior of A. This is our objective. When you want to show that two sets are equal, you have to show that A is a subset of interior of A. Also, interior of A is a subset of A. How prove karu pade? This we need to prove. So if you want to prove this two statement, one of them is trivial. Which one is trivial? Clearly, which one is trivial from these two? A is a subset of interior of A, or interior of A is a subset of A? You just see the definition of interior of A. What is interior of A? It is a set of all points in A such that there exists R greater than 0 such that SR of X is a subset of A. So what is this statement says? X belongs to A. So this set is always a subset of A. So clearly interior of A is a subset of A. This is straightforward. Now we need to prove this. So it is enough to prove this statement. A is a subset of interior of A. So I have to take one point in here and I have to show that that point is in interior. So let X belongs to A. But what is given as A is an open? We have assumed A is open set. So as A is open, there exists an R greater than 0. There exists one open sphere of this point X, SR of X, which is subset of A. But this statement gives you X is an interior point of A. So therefore, X belongs to interior of A. So therefore, A is a subset of interior of A. So from, if I call this is the statement 2, and this one is statement 1, then from 1 and 2, A equal to interior of A, which completes the proof of this. Now there are other certain results on interiors are there. I will state that result here and I will give you time of 1 day to prove that statements. So all the statement is for interior. X is a metric space which we require. The first statement is interior of phi is phi. Second statement is interior of X is X. Third statement is interior of A, which will be interior of A. The fourth statement is interior of A union B, I'm making space here, so you can fill this space. What will be the interior of A union interior of B? Whether you will have equality, subset, or other sign. Okay, you just think for that. Same way, interior of A intersection B. Also here I am making space. Interior of A intersection interior of B. Also you can think for this, which sign should be here. Whether it is equality is there or subset is there or whatever you want. Or there is no equality, there will never be equal. Okay? And the sixth statement, that is if A is a subset of B, which implies interior of A is subset of interior of B. So I am giving you this sixth statement to prove yourself. I give you 1 day time to discuss this problem. Okay. So now I can ask you, if you have any question, you can ask. Regarding this.